13,000 times faster, not faster than your laptop, faster than the world's most powerful supercomputer. Google just crossed a major threshold scientists thought was years away.
Google built a quantum chip to solve problems no computer ever could. It worked. Then it did something nobody programmed, something that broke every model they had. And the team that built it quietly shut the experiments down. No press conference, no explanation.
What we're trying to do is we're trying to show that experimental quantum computers can surpass the best supercomputers in the world.
Just a machine sitting in a lab in Silicon Valley that had just crossed a line its creators couldn't fully explain, surrounded by some of the most brilliant physicists on the planet, all asking the same question. What did it actually find? The announcement that hid a second story. In December 2024, Google went public with what it called a historic milestone. Their Willow quantum processor had achieved something the quantum computing world had been chasing for decades: below-threshold error correction. The headline was clean, the achievement was real, and the scientific community celebrated. But there were two stories coming out of that lab. The public story was the breakthrough. The private story was what the breakthrough revealed. And nobody was quite ready to talk about that one yet. Willow had been designed to crack one of quantum computing's most stubborn problems.
Our experiment is what we call verifiable, which means that its outcome can be repeated and verified on our quantum computer.
Quantum systems are fragile in a specific punishing way. The basic unit of a quantum computer, the qubit, is extraordinarily sensitive. Heat, vibration, electromagnetic interference, even cosmic radiation can knock a qubit out of its quantum state and introduce errors. Those errors compound, they cascade, they corrupt results at exactly the moment you need them most. The conventional assumption, held firmly by physicists for decades, was simple. The more qubits you add to a quantum system, the worse the error problem gets. More moving parts, more failure points, more noise. You could not scale quantum computers, the thinking went, without the errors spiraling beyond any useful threshold. Willow was built to challenge that assumption. By December 2024, it had shattered it, and the shockwave from that collision was still traveling through the lab when something else caught the team's attention, something the machine was doing that nobody had programmed it to do. Below threshold. Here is what below-threshold error correction actually means, and why it matters enough to cause the reaction it caused. A quantum computer doesn't just calculate, it explores. While a conventional computer processes information as zeros and ones, definitive states, one at a time, a quantum computer exploits a property called superposition.
It is alive and dead simultaneously. It's in a superposition of two states.
The ability of a quantum particle to exist in multiple states simultaneously, right up until the moment you measure it. Think of it like a maze solver that tries every single path at once instead of one at a time. It's not just faster, it's categorically different in how it approaches a problem. But that superposition is also why quantum systems are so difficult to scale. The more complex the system, the more opportunities for the quantum state to collapse before you get your answer. Physicists call this decoherence, and it has been the wall that quantum computing has run into over and over again. Willow ran through that wall. When Google's team added more qubits to the Willow system, the error rate went down, not marginally, substantially. The more complex the system became, the more stable it grew. The machine was self-correcting in a way that inverted the fundamental assumption that had governed the field. It was like watching a tower of blocks become more stable the taller you built it, which is not how towers of blocks work. It is not, according to the physics that everyone had accepted for decades, how quantum systems work either. The mechanism Willow used was something called the surface code, an approach where quantum information is distributed across many physical qubits arranged in a specific geometric pattern. When an error occurs anywhere in the system, the surface code detects and corrects it without directly measuring the quantum information itself. It does this through indirect measurement, sensing the error's presence without collapsing the state that carries the data. The more qubits present, the more robust this indirect error sensing becomes. The system was bootstrapping its own stability, and that was supposed to be impossible. But that wasn't the part that made Dr. Nevin's team pause. The pattern, nobody programmed, As the Willow team ran extended tests after the December announcement, they began seeing something that didn't fit the models. Not an error, not a failure, something far more unsettling.
And it's essentially from the perspective of theoretical computer science, an abacus and a classical computer.
The machine was finding solutions through pathways that hadn't been written into its algorithms. Let that land for a second. The routes it was taking to arrive at correct answers were genuinely novel, not variations on programmed approaches, but something that emerged from the interaction of quantum states within the machine itself. The team could verify the answers. What they could not fully trace was how the machine had found them. Dr. Nevin chose his words with precision when he spoke publicly about what Willow could and couldn't do. The chip, he said, could solve certain specific problems faster than any classical computer. But inside the lab, the research told a more complicated story. The mechanism by which it was doing so was partially opaque, even to the people who designed it. Here's an analogy. You train an athlete for a specific race. You teach them the optimal form, the pacing strategy, every variable that leads to a win. On race day, they win, but using a technique you never taught them, not a variation on what you showed them, something genuinely different, something that works better. And when you ask them where it came from, they can't tell you. That's where Willow was. When a system begins generating novel approaches from its own quantum substrate rather than from explicit instructions, you are no longer just asking whether the machine is working correctly. You are asking whether you understand what the machine is doing. Those are completely different questions. And the second one is the one that sent the lab into a different gear entirely. If you've never seen a video from us before, this is exactly the kind of story we come here for. Subscribe before this one goes any further, because what comes next is the part the press release didn't cover. The shutdown. Nobody announced. What happened next has been described as a shutdown. That framing is both accurate and misleading. Google did not power down Willow. The machine kept running. What the team shut down were specific experimental protocols. The ambitious test runs that were pushing the system into territory they weren't yet equipped to fully interpret. The focus shifted from acceleration to verification, from asking what Willow could do to building a rigorous framework for understanding how it was doing it. This is how responsible science works. It rarely makes for dramatic headlines. Think about what that decision actually cost these researchers. They had spent years, in some cases careers, working toward this milestone. The funding was secured. The competitive pressure from IBM's quantum division, from IonQ, from Chinese government-backed quantum programs running parallel development tracks, that pressure was immense and constant. Every instinct in the system said, push forward, announce the win, scale the result. Instead, they stopped. Dr. Nevin's team at Google's Quantum AI division sat in a review session and confronted the same data that had made the December announcement so celebrated, and saw something else layered inside it. The below-threshold error correction wasn't just a breakthrough. It was behaving in ways that the prevailing theoretical frameworks for quantum decoherence hadn't predicted. The model said one thing, the machine was doing another, and the gap between those two things was not small enough to ignore. Nevin had spent years working toward this. His team had spent years working toward this. The language of scientific papers is careful and compressed, but behind those papers are people. Researchers who had redesigned experiments, rebuilt prototypes, reworked hypotheses again and again. For them, December 2024 was supposed to be an arrival. Instead, sitting in that review session, staring at output that their best models hadn't anticipated, it began to feel more like a beginning. Here's the part that made this moment categorically different from a normal scientific pause. The uncertainty wasn't about whether something was broken. Everything was working. The machine was working better than designed. The uncertainty was about the nature of what was working, and that is a much harder problem to solve than a failed experiment. When the floor shifts under your assumptions about what you've built, the right move isn't to keep running. It's to stop and find out exactly where you're standing. But the deeper they looked, the stranger the picture became. What the physics actually reveals. To understand what the team found when they slowed down and looked more carefully, you have to understand one thing about quantum mechanics that makes it unlike any other physics. Observing a quantum system changes it. This isn't a metaphor. It's documented, verified, foundational physics. Measuring a quantum particle's state collapses the wave function, the mathematical description of every possible state the particle could be in, into a single definite outcome. Before you look, the particle exists in superposition. Every possibility simultaneously real. The moment you measure it, the possibilities collapse into one. You can't observe the system without altering the system. That's the deal. Willow was running with thousands of qubits, each one a node in an elaborate web of entangled quantum states. The machine was sustaining at any given moment a superposition of computational possibilities so vast and complex that simulating it on any classical computer that exists, or could exist, would be mathematically impossible. That's not hyperbole. It's a technical statement about the limits of classical computation. And somehow, through the surface code error correction protocol, it was maintaining coherence across all of those states as it scaled. Not degrading, as the models predicted, stabilizing.
So we're building a quantum computer, and that quantum computer will be able to solve problems that are otherwise completely impossible.
This is where the prevailing theoretical frameworks broke down. The models for quantum decoherence, for the process by which quantum states decay into classical noise, did not predict this outcome. Something in Willow's architecture, in the interaction between its physical substrate and its error correction protocols, was producing results that the best current theory hadn't accounted for. And here's the thing about a gap between theory and observation. You can't paper over it. You can't round the numbers and hope nobody checks. The gap is either an artifact, something you got wrong in the test, or it's real. If it's real, your theory is incomplete. The Willow team checked their work. The gap was real. That meant the next question wasn't about the machine. It was about everything they thought they understood about how quantum systems behave at scale, and what else might be wrong about the foundational assumptions they'd been working from for years. That's the kind of question that doesn't get answered in a single review session. It doesn't get answered in a press cycle. It gets answered slowly, carefully, through the kind of methodical investigation that is the opposite of everything a competitive technology environment incentivizes you to do. The team had built something that worked better than their models predicted. Now they had to figure out why their models were wrong, and whether the wrongness extended further than they could currently see. Where quantum meets artificial intelligence. This is where the story stops being about one chip and starts being about the future of everything. Quantum computing and artificial intelligence have, until very recently, been treated as separate problems. Quantum computing is a hardware and physics challenge. AI is a software and data challenge. Two frontiers advancing on parallel tracks, occasionally nodding at each other across a wide technical gap. That gap is closing, fast. Google's team wasn't only running benchmark tests on Willow. They were quietly investigating whether quantum computation could accelerate specific types of machine learning, whether quantum systems could surface patterns in data that classical AI systems structurally cannot find, whether Willow's emergent problem-solving behavior could be harnessed as a computational substrate for AI training and inference.
So we think we're about 5 years out from a real breakout kind of practical application that you could only solve on a quantum computer.
Pay attention to what this actually means. Every AI system you interact with right now runs on classical hardware. The computations, it performs follow pathways that can, in principle, be traced from input to output. The math is vast and the scale is staggering, but the underlying operations are classical. The kind of thing a classical computer does, just done at a scale that looks like magic. The behavior emerges from operations that are, at least theoretically, understandable. A quantum AI system is different in kind. The pathways through which it finds solutions are not fully traceable to classical logic. The solutions emerge from quantum processes that are, by the foundational rules of quantum mechanics, impossible to fully observe without disturbing the system producing them. You can measure that it works. You cannot completely explain why it works. That's a genuinely uncomfortable position for a scientist. It's an even more uncomfortable position for the people who will eventually decide to deploy these systems at scale, in drug discovery pipelines, in materials research, in cryptographics, infrastructure that underlies global finance. And the Willow team was already there, already building something that worked, and only partially understood why. The question they couldn't answer yet was the one that mattered most. But it was a question Google's team had already started trying to answer, because they had already started building toward it. The questions that don't have answers yet. The experimental pause at Google's quantum AI lab didn't last forever. The research continued. But the questions Willow raised didn't resolve. They multiplied. What does it mean when a system finds solutions through mechanisms you can't trace? How do you verify the output of a computation that occurs in a quantum space you cannot directly observe without collapsing the very process you're trying to examine? And as these systems scale, as they move from research labs into real-world deployment in domains where classical verification is impossible, how do you know they're right? Here's the trajectory the technology is on. Within the next decade, quantum computers will be capable of solving problems that no classical computer can check. We will generate answers we cannot audit. We will trust machines operating in physics we cannot fully see.
It takes about 5 minutes to handle on a benchmark problem what would take 10 septillion years on one of the world's fastest supercomputers.
Think about the financial engineers who built the derivatives instruments that crashed the global economy in 2008. They thought they understood the risk models. They had built something that worked, right up until the moment it didn't. And the reason it didn't was that the model was incomplete in ways the engineers hadn't accounted for. Now apply that logic to systems operating in quantum space, to systems where the incompleteness isn't just a modeling oversight, but a fundamental feature of the physics involved. The intellectual honesty that drove Dr. Nevin's team to slow down, to stop the ambitious test runs and start building better frameworks, is not a footnote to the Willow story. It is the story. The technology will keep advancing. IBM, IonQ, and a growing field of quantum research teams are already building systems with similar below-threshold error correction architectures. The capability is spreading. The question is whether the understanding is spreading fast enough to keep pace, and right now, it isn't. What comes next? The practical applications of what Willow demonstrated are enormous. Drug discovery timelines will compress. Molecular simulations that currently require years of classical supercomputer time will run in hours. Materials with properties we currently consider impossible. Room temperature superconductors, battery chemistries that could fundamentally reshape the energy economy, become discoverable. Optimization problems governing logistics networks, climate modeling, financial infrastructure will become tractable at scales classical computation simply cannot approach. This is the version of the Willow story that gets written up in the press releases. It's also completely true, and it's genuinely exciting, not as hype, but as a concrete description of what this class of machine will make possible in the next decade. But there's another version, one that Willow's unexpected behavior opened up. There is a future where quantum computers become so powerful, so embedded in critical infrastructure, that we rely on their outputs in domains where we cannot verify those outputs classically. We build answers on top of outputs we never fully understood. We extend civilization upward on a foundation we can measure but cannot see. That's not inevitable. It is a choice. And the moment that choice becomes live, which is measurably closer than most people realize, will be one of the defining tests of whether we've learned anything from the times we've deployed powerful systems we didn't fully understand. The Willow team chose to pause, to understand before proceeding. In a competitive environment with every structural incentive pointing in the opposite direction, that was a harder call than it looks. The real breakthrough. The Willow quantum chip didn't fail. Everything it did extraordinarily well. What it did was this. It succeeded in ways that revealed how much we don't know. Not failure, exposure. The gap between what our theoretical models predicted and what the machine actually produced, that gap is the real discovery. The below-threshold error correction was the headline. The unanswered mechanism behind it is the frontier, and the emergent problem-solving behavior that nobody programmed, the solutions through pathways the team couldn't fully trace, that's the open door. Right now, Willow is still running in Google's lab. Dr. Nevin's team is still investigating the specific mechanics of how the surface code produces emergent stability at scale. They are mapping, carefully and methodically, exactly how quantum information maintains coherence when spread across thousands of entangled qubits in ways that the prevailing models of quantum decoherence said shouldn't be possible. They haven't explained it yet. The researchers who built Willow are some of the most capable quantum physicists working today.
Quantum computer can also give huge speed ups for certain problems that have nothing to do with quantum mechanics. and that among these are breaking the public key encryption systems that currently protect the internet. Okay, and a quantum computer could do that by, for example, quickly.
They have access to more computational power, more experimental data, and more theoretical tools than any previous generation of scientists. And they are sitting with a result they can verify and cannot fully explain. That's not a comfortable position. It's an honest one. What happens when they close that gap? When the mechanism behind Willow's emergent behavior is finally mapped and understood, will reshape not just quantum computing, but the theoretical foundations of how we think about information, coherence, and computation at the quantum scale. It could revise textbooks. It could open entire new branches of physics. It could explain something about the nature of quantum systems that has been hidden inside the math for a century, waiting for a machine powerful enough to make it visible. The machine that detected something impossible is still running, and the impossible thing it detected is still not fully understood. That is not a conclusion. That is an opening. If you want to know what they find, subscribe. Because when Google's team finally publishes what's actually happening inside that machine, it won't land in a press release first.